Hi everyone, my name is Locke, and I will be presenting our work on interpretable and trustworthy deepfake detection via dynamic prototypes. This is joint work with Michael, Surisha, and Professor Yan Liu within the Melody Lab at USC. As AI continues to play a major role in changing many industries, it has also been used to generate and spread malicious misinformation. Deepfake videos, which can be utilized to alter the identity of a person in a video, have emerged as one of the most sinister forms of misinformation, posing a significant threat to communities around the world. To address this problem, a series of excellent works have been conducted on detecting deepfakes, achieving good progress toward the prediction task to a certain extent. However, very few of them address the interpretability and trustworthiness aspects. Currently, most existing approaches analyze the video frame by frame and drawing bounding boxes around a face, labeling it with fakeness probabilities. We argue that it might be more fruitful to explain why a model predicts a face as fake or real, which part of the face is believed to be forged, what inconsistency did the model learn, and where can we see an example of such inconsistencies. Our work proposed Dynamic Prototype Network, an interpretable prototype-based neural network that captures dynamic features, like unnatural movements and temporal artifacts, and uses them to explain why a particular prediction was made. Our framework has four main components. First, in the feature encoder, spatial and temporal informations are simultaneously processed via the high-resolution network architecture with pre-trained weights and cross-modality pre-training to average and increase the number of channels in the first convolutional layer. Second, in the prototype layer, the network learns M prototypes per class. Each is used to represent some prototypical activation pattern within the convolutional feature maps. This in turn corresponds to some prototypical dynamic pattern in the original video space. This is done by computing the squared L2 distance between each prototype vector Pj and each of the 1x1x patch of feature map Z. The distance is then inverted to retrieve similarity score. The scores are then fed into a fully connected layer, optimized for cross entropy, fidelity, separability, and diversity. To ground the representation so that they are interpretable, we project the prototype vectors to actual video patches from training videos after a few epochs. Lastly, traces from videos along with the prototypical activation pattern can be verified via the Temporal Logic module post-training. Given the direct computational path of the prototypes, we define specifications to check the robustness and temporal behavior of our model using time-quality temporal logic, short as TQTL. We verify that if our model predicts fake for a testing video, that throughout the video there exists a clip starting at time t where a prototype representing fake dynamics is most similar to it compared to all prototypes representing real dynamics for all time t prime in the video. This verifies that there exists a key region within the video that our models observe fakeness strongly. Moreover, we can specify that if a prototype is non-relevant, its similarity to a frame should be consistently low throughout the video. An example of this safety verification is that a prototype representing fake temporal artifact should not be highly activated in a real video at any time. Our network makes predictions about face forgery by exploiting temporal artifacts, which are harder to hide and can generalize across different manipulations in the RTP Pixel space. We train and test with 4 manipulation types from Face Forensic++ on both high quality and low quality compressions. We look at different evaluation metrics such as AUC and other global metrics at a low false alarm rate. In general, our approach has superior performance compared to exception and two-branch. Notably, exception and two-branch does not offer any form of intrinsic interpretability. For cross-dataset evaluations, we report a clear net improvement over the state-of-the-art baselines with zero extra training data, getting 1 to 4% increase in AUC across the board, even for manipulations with real-world perturbations like deepfake forensics and low visual artifacts such as CelebDF. We also visualize the prototypes and see that the network learns some artifacts such as heavy discolorations, subtle discoloration or movement, face juring, and unnatural oscillations, which are harder to interpret with just one frame. For more information, please feel free to stop by our poster session. Thank you.